welcome back to the hyperbolic coding chamber. This is day 65, a momentous day and occasion for the hyperbolic coding chamber, as well as all LeetCode doers and problem solvers. You might be wondering, why is today a momentous day? It is merely because today is day 65 of daily LeetCode. Pretty hype. So we're back once again. Yesterday we were working on symmetric tree. Right, we're still ducking on evaluate division. This problem, I'm not convinced is solvable. Right, symmetric tree, I think we just ran out of brain juice. Right, and we just got stuck in. We know how to solve this iteratively. There's a follow-up to solve it iteratively. We know how to do it, but I was just trying to figure it out. Other things, though, right? We have some problems due today, and yeah, I have to be honest. I read the system. I was going through Don Martin's System Design Primer. This is a must cop, a must read. This is a legendary tool. I finished David Mallon's lecture on systems in general and scalability. I mean, the man is that lecture itself is a master class in teaching, right? The way he works down topics, the way he talks to the students, right? He incites just deep thought, and he has good questions, right? But you never feel like he's beating you over the head with a lesson, so that's pretty dope. And then I think there's a study guide primer, right, in this repo. It basically tells you how to go about going through this. I'm pretty much at the point where I'm reading through company engineering blogs. So yesterday we read about Quora, and what did Quora do? I don't even remember what they did, to be honest. So I started doing, so now that I read for 30 minutes, I'm doing at the end for the 5, right? I try to do like just like a review, right? Like, what did I learn? Like, as I'm reading, I'll just stop and be like, okay, what does this mean, right? If I think for a second, Quora was trying to fix something. They were trying to fix something, and they fixed it. That's what I got from that blog, right? But to be honest, I think there was a lot of jargon they were using I just didn't understand. So I think it was just like a brain differential. But I was reading about Etsy's system design primer. I mean, Etsy's Code as Craft blog, legendary blog as well, right? And they were talking about their blue-green deployment strategies and how they like implemented a special version of Canary deployments by using pretty much a Canary Lite that they implemented called Switchboard. So that one I actually understood, so it was pretty cool to see the progress. And I think we're only like 4 days into learning system design, so that's pretty cool. I feel like I'm definitely understanding more. I think I'm certainly starting to see why Kubernetes might be a cheat code, so that is pretty cool. But yeah, I think there are big things coming for the hyperbolic coding chamber, so I'd like to switch up things a little bit, maybe do a stream once a week, also update the setup, and just some other things as well. I have some ideas for maybe changing just some things. So it is interesting as always. And as well, you're going to want to know, right, who our special guest is going to be tomorrow night. I'm just going to reveal it right now. It's Elon Musk again. So he joined the Discord. He's going to be live in the Discord tomorrow night. So you're going to want to join. This is actually true, right? And also just as true that there are hundreds of millions of people in the Discord as we speak right now. So if you click join the Discord in the YouTube description below, you're going to enter a queue. Well, it could take anywhere from 36 to 48 hours to join the Discord. So you're going to want to join, right? Lots of legendary studying resources in there, as well as methods, right, to go about studying, right? So we have really cool people join yesterday, right? Someone dropped a LinkedIn yesterday. It's just cool to connect with people, right? So that is pretty cool, right? So you're going to want to join. Additionally, I was reading the algorithm design manual, right? And legendary holy text written by Scanna himself. So I learned a new method for a BFS. And the goal there, right, is that there's a 3-tiered, or pretty much 3 spots to pretty much insert code, right? So I just found it, right? So this is what we're working with. This is a legendary piece of code we have here, right? And so there's actually 3 spots that you can actually insert some code. You kind of can't see it because, yeah, it's in the way. But if I move my mouse away, you can see on the bottom line, we have process vertex late right here, right? You have process edge. So let's process vertex early. These are absolute cheat codes, right? Because I'm probably certain that hundreds of problems are solvable with these 3 inner portions right here. That being the case, we're going to try and implement this version of the algorithm today, right, on a problem that I have in mind, right, called binary tree right side view. This is typically done with a BFS, right? But I'm curious to see if we can find a new way. And I think I just remembered, yeah, we can figure out a new way right now. So I think there's a new way that we can do it with this BFS algorithm. And I haven't really memorized this algorithm at all yet. The goal would be to actually have memorized it though. So earlier we memorized the union find data structure, right, after watching a video about it. So that would be pretty cool. And as always, that is the goal, right, to have as many different tools as we have in our back pocket so that we are unstoppable in the battlefield of logical prowess, right? It's us versus LeetCode. So yeah, that being the case, we're still on the grind for review. So ideally, I'd like to have, the goal isn't to have every single problem in spaced repetition. The goal is to have just the core problems, right? So I'd like to, the minimum, be in the habit of solving problems that I've solved before. And I think just in the last week or so, right? I think we can even see it now, right? With binary tree right side view, there's a new angle I want to try a BFS on. And this is kind of one of the magics of spaced repetition, right? Now we get to try this problem, right, in an environment that we're very familiar with, right? So we're very understanding, right, since we're about to apply this new method, of exactly what the difference is between our previous method and our new method, right? So what they offer us. So the cool thing is I could have tried this algorithm on a new problem, but then I wouldn't be able to juxtapose my previous solution with this one. So I guess that's really the fire moment there. That being said, we got to acknowledge our boys and fellow software peoples in the chat. I'm just that guy speaking the holy language. 10, 10, 10. I think this is 10. LeetCode. Either way, the message is coming across. 10 and LeetCode. LeetCode is amazing. Time flies when you're having fun with your LeetCode. Yeah, this is our boy Thomas. This man is doing 3 hours of LeetCode a day. Respect. Respect for that. That is very difficult. I think I used to do a similar amount, but my brain is just not there. Even yesterday, we were doing an hour, right? We were doing an hour yesterday, and after 45 minutes, I just start, nothing comes out. It's just dead. And it's interesting because I think actually my stamina might be a bit better now. But I'm also, by the time I start LeetCode, I'm about an hour after reading system design and ADM. So maybe we're close. We're about half of, if Thomas's skill levels is like over 9,000, maybe it's 9,001. We're at like 4,500, right? So we're catching up slowly but surely. But this is the man. Yesterday we dropped a video called Tortoise and Hare 2 Electric Boogaloo. I think today's video is going to be called Tortoise and Hare 3 : right? And this is going to be part of it's going to be called Tortoise and Hare 3, the movie, right? And so this is going to be the end of the Tortoise and Hare trilogy, right? Because the whole theme of the last 3 days has been that slow, right? To go fast, one must go slow. And so this would be the end of the trilogy, right? But we're going to reboot it, right, for the 5-part saga following the next day. But also, I'm going to be moving around the next few days, so the setup's going to change a little bit. So yeah, I think we have 1 hour on the clock, right? And also, yeah, if you have any ideas for maybe different ways to tackle problems, or maybe a different format, or if something like a stream would be a good idea, right, then feel free to drop me a line on Discord, right, and maybe we can figure something out. So yes, so we're gonna jump into it. I'm thinking the plan for today is I really want to get to binary tree right side view because I want to try the new BFS algorithm. Invert binary tree is typically done with a DFS. Actually, I'm lying. Invert binary tree can be done with is typically done. Actually, it could be done with either. Yeah, it could be done with either. So maybe we'll try it with the DFS. I don't know if we've ever tried it with the DFS. Symmetric tree is what we're working on yesterday, right? We wanted to do a BFS version of it, and then we have square root of x. So I'm wondering, right? Yeah, I think, okay, yeah. So I think this is what we'll do today. So don't forget to join the hyperbolic coding chamber. So yeah, we're gonna jump into it. We have an hour as per usual. So let's just do the thing. Right, so we have a tree, right? We want to know whether or not it is symmetric across itself. Originally, we did this with a recursive solution while propagating a sequence of Boolean expressions, right? The follow-up is, can you do this iteratively? We know that we can do this iteratively with an iterative BFS, right? But the version we're going for here is to create the BFS, to create that array here, right? And maybe impose some level-based ordering on this array, just to see if there's another nugget we can extract from this problem. I'm sure knowing how to do this could be useful in the future. Right, but we have a problem, I think, if we run this code, right, for a simple tree, right, like 1, 2, right, we'll have for example, let's just ignore the right half side of this tree, right, we'll have q equals root, right, so we're at 1. The q isn't empty, so we're going to pull the root off of the q, right? Now, if the current node is equal to undefined, right, then we're going to push onto the array. Well, it's not, right, because it's 1. So we're going to push the current value, which is 1, and then push its left child. Its left child is going to be 2, so you said we're going to ignore the right-hand side. Does cur.left equal null? It doesn't, right? So we're going to push cur.left onto the queue. So now you have 2 on the queue, right? So I guess if this is the test case that we're using, right, let's insert that in here. So we have 1, 2. We want to remove this 2 because it would be null actually. Then we'd have null in 3. Then I think it would actually be like this. So we have 1, 2, right? Null, null, and 3. That's what it would look like. Right, so then we pull 2 off of the queue, right? Does 2 equal undefined? No. So we're going to push 2 as an array, as a value onto the array. Then we're going to push onto the queue if cur.left equals null. Now, does cur.left equal null? It does, so we're going to push undefined onto the queue. Interesting. Right? And then we're going to push 3. So we have undefined and 3 on the queue. Right, so the next thing we're going to do, we're going to pull undefined off of the queue. Right? And if cur equals undefined, right, then we're going to push null onto the array. Right, which makes sense. I'm not sure why we have this continue here if we have an if and an else. So that's a bit strange. Right, so we should have null. And the thing that's remaining on the queue should be 3. Now I see what's going on. When we get to, so we get 3, right? 3 is not undefined, right? So we end up pushing on null and null. We only want to push this. I see what's going on now, right? If our queue is empty, right, then we'd want, if our queue is not empty, then we want to push if our queue is not empty and our children don't exist, then we don't want to push anything on, right? We want to stop. That's why we're ending up with extra, I believe. So I think if we run this, we should end up with 2 extra nulls. We do, we end up with 2 extra nulls. So I think that means is, right, we can just do something like this, cur.left, right, and cur.right, right, and we'll do for each node. We're gonna have an if statement, right, and we're gonna say, okay, if cur.left does not, all right, if it equals null, right, and q.length and q.length does not equal 0, right, then we want to do q.push null, right? Else if cur.left does not equal null, right, then we want to do q.push. I said cur.left, what we actually mean is node. I'll make this bigger. So that this makes more sense. Then we can do q.push the node, right? And otherwise, we actually aren't interested otherwise. So I think now if we run code, okay, so this is another problem, right? We want it to default to null, right? And so I think this should fix the problem of us having and we actually don't want to, okay. There's a few things going on here. We actually want to push on undefined. Now we're getting what we're looking for. 1, 2, null, null, 3. This is really convoluted, and I think going into the future, right, we're going to need a better way to go about this, because this would be very confusing to reason about in a problem we haven't seen before. But also, I thought it might be good practice to be able to, actually, because it's easier to get this array, right, without the null values, but it's harder to get it with it. And so now I want to see if our version works, right? The original intuition for this, right, was that now that we have this array, right, for this output, now that we have this array for this output, right, I wanted to know if we could employ a simple technique to check whether or not the values, if we could do this based on an array, right? So we know to start that our level is equal to 1, right? So if that's the case, we start at I equals 0, right? And we do, right, to check left and right, we'll say, okay. Or we could start at level equals 0. So if we bring this all the way down, right, if we start at level equals 0, right, now we can say, check that node to the left of me, it's going to be I plus level, which is 0 plus 1, which is 2, and to the right of me, which is I plus level plus 2, which is going to be index 2, right? 0, 1, 2. Are the values the same? They are, right? And then we can increment 2 from there. So we can go from here to here, right? Actually, no, we don't want to increment 2. We go to 2, right? And now I want to check if both of these values are null, right? So now level would be equal to 1, right? So we'd say level plus 1 plus 1, level 2 plus index 1 plus 1 plus 1 equals null, and level equals 1 plus 2, so 3, 0, 1, 2, 3, right? And they're not the same, so we want to return false. Now if we do the same thing here with 2, right? We do 1 plus 1, we do right, we'd say 2, right, plus, I want to get all the way over here, just 2 nodes. So maybe what if we just say how large I is, right? So if we start at I, right, I is equal to 0, 1, 2 here. So if we do move over 2, like 1, 2, right, we add 1, it's going to give us null. And if we add 2, it's going to give us 3. So if we do this one, we start at 0, right? I is equal to 0, right, plus 1, plus 2. Now I equal to 1, add 1, right, we can check 1 and 2. Then here, I is equal to 2, we can add I, right, which is going to be 2. Right, and we can check this and this. So what if that is how we check, right? We pretty much want to check over the r dot length, right? I plus plus. We want to say if r sub I, all right, and we kind of want to exclude the root basically. So we can actually start at 1. Which is going to be 2, right? And then here we'll just say if, all right, if r sub 1, right, does not equal r sub 2, right, then we'll return false. Actually, we don't have to do that because that's going to be checked right here. So we'll say if r sub I, right, does not equal, right, r sub I, right, plus I, right, so it'll be here where I would say index 1 plus 1 give us 2, right, plus 1, right, or I can actually duplicate this. I just want to see if I'm blocking anything. I'm not. Right, but here I'm actually going to say I plus 2, right? Then we want to return false. Then we won't have to use this level thing. So I'm curious if this makes sense. So it works on that case. All right, let's see if it works on a case that makes more sense. It looks like the array we're producing here makes no sense. Maybe it does. We have 1, 2, 2, 3, 4, 4, 3. And then we have a lot of nulls. how many extra nulls do we have again? Right, if we have 1, 2, 3, 4, 5, 6, 7. We have 7 basically. If the node is null, I think a better idea might be if cur exists, right, and not node, right, then we want to push undefined. That way we can say else if node exists, right, then we'll push it. I think this is the problem, right? 3 does exist and its child doesn't exist. So it does end up still pushing it on anyway. This is a little silly. This is the case we saw for earlier, right? If 2 exists and its child doesn't exist, then we just push on undefined. And q.length isn't empty, right? Because that's what we're interested in, right? That we still have nodes within the tree. Problem is when we're at the end of the tree, we don't want that. I think another thing that's strange is you'd expect that there would be, no, there are 8 nulls. So it's literally what's happening at the end here. There are 8 nulls down here. All of these are producing I mean, there is one thing we could do, right? And this is just silly at this point, but we could just say that while r.length doesn't equal 0 and r sub r.length minus 1, the last element does not exist, right? Then we can just do r.pop. Just pop the last element. So let me print what that array looks like after. So it looks like we get the goal output here, but our algorithm still fails. So let's see. All right, we start at I equals 1, so 2, right? While I is less than, all right, let me check if r sub I does not equal r sub I. So we go to I plus I is 2, right? Plus 1. I think the second half is messing us up, right? They're checking that if these two match, right? Then we go to this 2, right? So we can't necessarily increment by 1 if we know that they already match. We then like to go to this 3, right? This first 3, we'd like to check 0, 1, 2, 3, right? This 3, right, plus 3, boom, boom, boom. 0, 1, 0, 1, 2, 3. Yeah, I'm thinking closer now. We should have just made sure that the original idea worked, because I'm thinking that this method of checking the array is nonsensical. 2, 2. Or maybe it could work. One last check, right? Once we get to an index, I want to check that the 2 subtrees make sense, or the 2 parent nodes make sense. That's what we're doing up here. Now that we have the 2 parent nodes, right, we want to make sure that their children are mirrors of each other. So then we go to the left child, right? To get that left child's position, that would be I plus 1, which would be 3. Right, and to get that right child's position, it would be 4. Now, if we have that right pos, right, it would be 0, 1, 2. 2 plus 2 is 4. 0, 1, 2, 3, 4. Right, and then the goal after that, what would the goal after that be? What would you even increment? After that, ultimately this algorithm is just too convoluted, but it was an interesting experiment. I think we should just go for the regular queue-based BFS idea, right? And what we'll do is we'll just do a level order traversal, right? We'll push 2 and 2 onto the queue. If we have these 2 on the queue, right, then we want to make sure that their children make sense, and we could push this node's left node and this node's right node onto the queue together, and then these two together and these two together. Right, that way, so we move through the queue would actually be, we actually doing a BFS when we pull off two nodes at the same time. So maybe we could do something like that. We'll say, well, queue.length is not equal to 0. Right, and we'll say left and right is equal to queue.shift. Right, so we'll pull those two off. Right, we'll say right, so we want to check if their values aren't the same. So we say if left.val does not equal right.val, right, then we want to return false. If the values aren't the same, we want to return false, right? If they are the same, that's good. So maybe we can now push on to the queue left.left, right, with right.right, and left.right with right.left. We should be able to have that keep going long term. Right? But what if, one of these doesn't exist? Right? Then what we'll do is we will if we look at it this one, right, we push 2 and 2 onto the queue, right, pull them both off. So we actually would have to do, can't really be structure here. Or maybe we could do it this way, right? We could do an array of tuples, right? Then you could destructure them, and then we could have 2 and 2. Now, 2 and 2 are equal, right? So if we push on left and right onto the queue, we're going to have pretty much null and 3. Now we're going to pull those off next, and we're going to say, are they different? They are. Return false. What if they're both null, though? If they're both null, then they won't be different, right? So we would keep going. So I guess the other thing you want to check just to be sure, right, is if left, if not left, right, and not right, then we'll just continue. Because in this case, right, we want to push left dot left, right? Like we said, we're doing an array of tuples, so left dot left, right dot right. Then we want to do left dot right with right dot left. If we make it all the way out here, maybe we can assume that we're true. So before we run this, so we're not guessing, all right, we have 1, we push 2 and 2 on, they're not different, they both exist. Right, so we push on left, we push on null and 3, then we pull off null and 3, right? They don't equal, they're not the same, right? But let's just say they were both different, they're both null, we pulled them both off, they're not different, so we continue, but they both don't exist, so we would continue. So I think this could work. Because we could safely navigate. So this does work. So I'm glad that works. So I think we're pretty much good there. I spent a lot of time on that, but that's fine. And we're working on symmetric tree. So now I really wanted to try the new BFS algorithm, so we can do that with binary tree right side view. It's given the root of a binary tree. Imagine yourself standing on the right side of it. Turn the values of the nodes you can see ordered from top to bottom. So we have this binary tree here, right? And they want us to return the view of it as if we were looking at it from the right side. That looks like 1, 3, and 4. And presumably, if 4 was missing here, we'd actually have 5 here. So this question, in another sense, is asking us to do a level order traversal, but print the last. Oh, my neck hurts. A level order traversal. A level order traversal will print the last node in the level. So this would be 1, 3, and 4. So if that's the case, right, the new version of the BFS wouldn't exactly give us better access to what we're looking for here, because what we want to know is the last node in the level. Right, and with that function, with that new version, right, we pretty much have 3 spots, right? Process vertex early, which is when we first visit it, right? 1, and process vertex late, right? Which is when we're moving on. So for example, if we just added something to the level, right, at the end of process vertex late, right, that would be the last node in the level in the sense of the first root node, but would it be the last node in the level if we're doing 2 and 3, right? So we have pushed 2 and 3 onto the queue, right? Process 2, or we would discover 2 and then begin processing it. 5 onto the queue, but then we process the vertex late, so it wouldn't exactly be the last one either. So maybe there's another version of this function we can implement where we also have access to the level. Right, so let's just try for the sake of implementing it, right? ADM BFS augmented with process level, right? And so I think this version requires 3 arrays, right? You need the discovered array, right? And we'll probably create a function so we can initialize these values. But additionally, right, these 3 arrays usually have they're usually like an array of Boolean flags, right? So typically we need to know how many elements to have for this array of Boolean flags. So maybe we could do the same thing. Can we assume that every node is unique? It's actually uncertain. You cannot know if every node is unique. Right, and I think this is kind of a problem with the ADM's version of the BFS. I think you also need it in the form of an adjacency list. Or maybe it doesn't work well with implicit graphs, because the implicit graph is one we're pretty much building as we have access to it. Problem doesn't say that all the nodes are distinct, which means we probably can't assume that they are. I mean, for other purposes, for all purposes, right? We have 3 arrays, right? We have discovered, right? We'd also have parent, right? And we'd also have processed. Process just lets us know when we've processed the node. Functionally, we could swap these out for sets, right? But we don't know if these nodes are distinct. Since we don't know if they're distinct or not, it's actually a bit hard. That being the case, I'm realizing that this version of the BFS, we're really only concerned with the levels, and we kind of need to know that each node is distinct, at least to some respect, to be able to tell. In another language, we could do this, right? Because TypeScript, we don't really have an access to the memory. But if we had the memory address, then this would also be solvable because we could just use that in the set. Let me see. So I was looking up if there's a way to know if we can do this in JavaScript with like pretty much defining memory. I mean, looking at it where an object is stored in memory to uniquely identify it. So looks like that is not possible. So we could do something where we wrap the object or we add a property called ID to it. This would not work well in TypeScript just because this type is already defined. We could extend it. If we extended it, it is possible that we could use the new BFS, right? And so anytime we see it for the first time, we'll just add we'll pretty much just add a ID variable to it. That's another layer though. We're managing IDs. JavaScript is truly a mess. So if we see if we see the root node for the first time, we started with an ID, right? ID plus plus. Right. Right, I would have to check if it doesn't have a property and then give it one. Right, so maybe we can go with that. Right, so we'll say let ID equals 0. Right, that way we can change discovered and processed. Right, we'll change these to sets, right, of numbers, and that's how we'll know, right, if we've discovered or processed a node already. Right, and I'm pretty sure to start, right, if our tree is empty, we're just going to return an empty array. But to start, right, we're going to need, the parent is for plotting the path between the nodes, but we're going to have a queue, right, which is going to have a root node within it, which also means that to start, right, we can do discovered, right, dot add ID 0. And additionally, we can say root dot ID is equal to ID plus plus. Right, and then here we'll just say that instead of a tree node, we'll just have a unique tree node, right? We'll say interface unique tree node extends tree node, and then we'll just have ID, which is going to be a number, right? And I'm just curious to see if that works. Just return an array. We have access to change it in this LeetCode problem, so we can just say that it's going to be a unique tree node. So it looks like this does work to start, right? So now we can just implement it, right? So I think the way it works is while the queue is not empty, right, we're going to have a couple things happen, right? We're going to have our vertice, right? It's going to be our vertice, right? So our vertice to start is going to be equal to q.shift. So now we have this vertice, right? I guess it's easier if we call it x and y, right? That way the node that we're currently at is always x, and the node that we're looking for is y, so component x and component y, right? And so for component x, right, if, and we just have to do something, right, we can actually define a function, right, that we can call, we can just call a function that modifies state called addID, and it's going to take a node, which is going to be a unique tree node, right? It's not going to return anything, and it's just going to say if addID, if node, if object, right, does not have its own property, right, this property is going to be called ID, right, then we're going to say node.id equals ID plus plus. Right, then we'll add the ID. It already has an ID, so it actually doesn't matter. We can actually remove this line here. So we'll give it an ID, right? And now there are a couple things we're going to do. We want to say that it's processed, so we can say processed.addX.id. And then there's also another spot here where we can say, like, right, process vertex early, right? But other than that, I think here's where we're going to visit neighbors, right? So to visit our neighbors, since this is a tree, we're just going to have left and right, right? So we'll say, let's take x dot left, right, and x dot right. We'll do a for each over it, and we'll just call it y. It'll be a unique tree node, right? And then we'll call addID for x dot left, right? And the other thing we want to make certain, right, is the node actually has to exist. If node, right? So we'll add an ID, right? And this is going to be called y. And the first thing we want to know, right, is if we've discovered, if we haven't discovered the node yet. I think it's if we haven't discovered the node yet, or the graph is directed. Graph is not directed. So if we haven't discovered this node yet, right? So if discovered does not have y.id, right? Then we can have something like process edge, right? And then we're just going to say edge, right? And we're going to say between x dot val, right, and y dot val, right, just to see if we have the right intuition here, right? And if we haven't discovered no, I think if we haven't processed. So if we haven't processed this node yet, then we want to pretty much take a look at this edge. No, I think it's discovered. Why would it be discovered? If we haven't discovered this node before, right, this will be the first time we're seeing this edge, right? Because presumably we'll have seen the other component already. So it's the first time we're seeing this edge. And we'll say if discovered does not have y.id, right? And we haven't processed. And we haven't processed it. We want to add it to the queue, right? So we'll say queue.push y, right? And then we're also going to say we discovered it, right? So we're going to say discovered.add y.id. And then we have that parent array, right, for managing or plotting the paths between nodes. We'd also have that here as well, right? And at the end, we could say process vertex late. There's definitely a lot of parts of this we can leave out, but it's just for the sake of the example. So let's see if we get the edges. Line 77 car 5. Line 77. So it looks like we're missing a curly brace likely. Definitely right here. As unique tree node array. We're reading underscore ID. Add ID to Y if the node exists, or and if it doesn't have. Line 44, card 3, line 44. So I think one thing we could also just do, right, I would say if not Y, continue. Oh, I guess we'll just say this only works, right, if the node exists. So our input array, we have an edge between 1 and 2, 1 and 3, 2 and 5, 3 and 4. So this is actually working very well. Very cool. All right, so we know the process edge is working correctly, and our graph is actually undirected. So we're actually not visiting each node. We're not actually printing it twice, right? So this is what the discover is helping for with here. Right? So if we haven't discovered it, right, then we can look at the edge once. But if we wanted to look at each edge twice, right, then I guess you could just take out is discovered here. We'd also end up going indefinitely though. Actually, no, we wouldn't. I think if we do take this out, we do still end. Okay, so looking at the other one, it's actually looking at the implementation. It's actually if we haven't processed it. We get similar output anyway. We processed it. And then this one is if we haven't discovered it. Well, this is a tree actually, so it actually is directed now that I'm realizing it. But either way, this still makes sense. So now I'm trying to see if there maybe is a location we can just sneak in a process level. Right, so let's just say we always added null. Right, we always added null. Right, that way we could know when we're done processing a level. Right, maybe we could have something like a level array. We have a level array, right? Whenever we take an element off the front, right, we can say level dot push x, right? And once we're finished, right, processing the vertex, well, this is different, right? So I think it would just be fusing the algorithm, right? It's if x, right? Then we'd shift all this over pretty much, right? That's one way to do it, right? And actually else down here is maybe where you could process add ID to x, right? And then we're gonna say level dot push x. And it's likely down here, right, where we could actually have our process level. So if that's the case, right, we want to do, right, is if the queue dot length does not equal 0, so if there are still nodes left, right, then we'd like to push onto the queue another null so we know when the level ends again. Additionally, we'll probably set level equal to an empty array again. Right, so I think we actually have this set up now. We'd have output, right? We could have something like this. Constant output is going to be an array as well. Instead of pushing the actual node onto the level, we're going to push the actual value at that node. That way, once you reach else, right, we can just say output dot push, and we're going to push the last node in the level. Level dot length minus 1. Level is indeed a constant. Nice. Oh my God. So this is good. It's still the same output as usual. The good part being that this one is much more robust, right? We can process vertexes late with specific spots. We can process them early. We can also process edges, right? Which we saw here. We process the edge, right? And we also have a place to process levels. So I envision in the future, right? This will be very, very useful. So I'm going to wrap it up there. So